Where the MGF becomes really useful is in the calculation of moments for sums of independent random variables. Here's the main theorem. For a collection of independent random variables x1 through xn, we can calculate the moment generating function of w, the sum of the xi's, in a really simple way. It's simply that the moment generating function of w is the product of the moment generating functions of the xi's. And in particular, when all of the xi's are IID and all of the xi's have the same moment generating function, then the moment generating function of w is just the moment generating function of x raised to the power n. The proof of this is really quite simple. We just write phi w of s, the moment generating function of w, is the expected value of e to the sw. And this is the expected value of e to the s x1 plus dot 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 plus xn. Now we can rewrite this as a set of products e to the power sx1, e to the sx2, and so on up to e to the sxn. And now, because the xi's are independent, the expectation of the product is the product of the expectations. And this gives us the products of the moment generating functions. You can use the theorem for calculating PMFs and simple moments of random variables, like in this example. Here, phi j of s is the expected value of e to the sj, and that's equal to 0.2 times e to the s plus 0.6 times e to the 2s plus 0.2 e to the 3s. And phi k of s is the expected value of e to the sk, and it's equal to 0.5 times e to the minus s plus 0.5 times e to the s. And now the moment generating function of m, which is the sum of j plus k when they're independent, is equal to phi j of s times phi k of s, product of the moment generating functions. And this gives us 0.2 e to the s plus 0.6 e to the 2s plus 0.2 e to the 3s, and now times 0.5 e to the minus s plus 0.5 e to the s. The result is that we get 0.1 plus 0.3 e to the s plus 0.1 e to the 2s plus 0.1 e to the 2s plus 0.3 e to the 3s plus 0.1 e to the 4s. And you combine all of these, and you get 0.1 plus 0.3 e to the s plus 0.2 e to the 2s plus 0.3 e to the 3s plus 0.1 e to the 4s. And from this MGF, you can simply read off the PMF of M. I can just write it down here. The PMF of M is equal to 0.1 at m equals 0, 0.3 at m equals 1, 0.2 at m equals 2, 0.3 at m equals 3, 0.1 at m equals 4, and 0 otherwise. The point is that the coefficients multiplying e to each power exactly correspond to the probabilities of this discrete random variable. Specifically, this 0.1 is this 0.1, and 0.3 at m equals 1 corresponds to this 0.3 multiplying e to the s, and 0.2 is this coefficient of e to the 2s, and so on. Taking derivatives and setting s equal to 0 will give you the moments of m. More than just doing calculations of moments, the MGF gives you simple proofs about the properties of certain sums of independent random variables. For example, here we have a theorem that says uh, if k1 through kn are independent Poisson random variables, then w, the sum of these, is also a Poisson random variable. To show this, we assume that ki is Poisson with parameter alpha I, and that means that its PMF is alpha I to the k, e to the minus alpha I over k factorial, for k equals 0, 1, 2, and so on, and 0 otherwise. Now we need the moment generating function, and this is equal to expected value of e to the ski. Of course, this is summation k equals 0 to infinity. E to the sk times the PMF, which is alpha I to the k, e to the minus alpha I over k factorial. You could just look up this MGF in the textbook, but it's more fun to work it out here. First, we factor out the e to the minus alpha I. Then we write the sum, k equals 0 to infinity. And then we realize that these two terms can be combined, and they become combined as alpha I e to the s raised to the power k over k factorial. And the next step is to say, if we call this combo term x, then what we have here is the Taylor series expansion of e to the x. And the result is we have e to the minus alpha I, e to the alpha I, e to the s. Now combining the exponentials, we get e to the alpha I times e to the s minus 1. And this is the usual way we write it. And it's a funny looking expression because in fact it's a double exponential. This e is raised to the power of this function, and this function includes another e to the s in it. However, now that we have the MGF of a Poisson random variable, we're ready to prove our theorem. The MGF of the sum phi w of s is equal to phi k1 of s times phi k2 of s. The product of these moment generating functions up to phi kn of s. And now we write these terms out. The first one is e to the alpha 1, e to the s minus 1. And the second one is e to the alpha 2, e to the s minus 1. This sequence of products continues up to e to the alpha n, e to the s minus 1. And now we can combine these exponential terms, and they actually combine in a nice simple way. It's alpha 1 plus alpha 2 plus dot 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 plus alpha n times e to the s minus 1. And if we define beta equal to alpha 1 plus alpha 2, the sum of the alphas we have the moment generating function of W is e to the beta e to the s minus 1. And now what we realize is that the moment generating function of W has exactly the same form as the moment generating function of each ki. The only difference is that with ki, the expected value is alpha I for the Poisson random variable. Now we have a Poisson MGF where the expected value is beta, the sum of the alphas. In the same way, we can prove that the sum of n independent Gaussian random variables, W is x1 sum up through xn, is also a Gaussian random variable. The first step is to find the moment generating function of each xi. To do this, we assume that xi is Gaussian with mean mu I and standard deviation sigma I. In this case, the moment generating function phi xi of s is equal to the expected value e to the s xi, and this is equal to the integral minus infinity to infinity e to the sx times the PDF of x, which, since we're all good with Gaussians, everyone can just write down e to the minus x minus mu I squared over 2 sigma I squared dx. Frankly, this integral is a big hairball. What you have to do is you have to take this exponential term and combine it with this exponential term. And then you have to follow a procedure where you do something called completing the square in the exponent and do some factorization. And eventually you'll get the right result. The steps are in the book, but we'll just jump to the conclusion. This moment generating function is e to the s mu I plus sigma I squared s squared over 2. With this result, we're ready to prove our claim. The moment generating function of W is equal to the product of the moment generating functions. And we can write these down. The first one is e to the s mu 1 plus sigma 1 squared s squared over 2. And the second term is e to the s mu 2 plus sigma 2 squared s squared over 2. And the last term is e to the s mu n plus sigma n squared s squared over 2. And once again, we have a product of exponentials, which we can combine into a single exponential whose exponent is the sum of the terms. So we get this is e to the s, and we have mu 1 plus all the way up through mu n plus sigma 1 squared plus all the way up the sum of the variance is through sigma n squared s squared over 2. And once again, we see what we expected to see. We see that W has the moment generating function of a Gaussian random variable. This form is exactly the same as this form, but the expected value is mu 1 plus mu 2, the sum of the mu i's, and the variance is the sum of the sigma I squareds. So what we have is that we've shown is that W is Gaussian, and the expected value is the sum of the expected values of the terms, and the variance is the sum of the variances. So this is a great result, and the moment generating function provides a really simple proof. But it's important to keep in mind that this result is true for independent Gaussian random variables. Earlier in chapter 5, we stated a result that for W equal to x1 plus x2, where x1 and x2 were bivariate Gaussian, that the sum W was also Gaussian. And this result in some way, because it applies for xi's that could be correlated, is a more powerful result because it could be extended to n random variables using induction. Nevertheless, the theorem here for a sum of independent Gaussian random variables is simple and super useful. Another result of this type is that if x1 through xn are IID exponential lambda random variables, then the sum W of x1 through xn has the Erlang PDF. In this case, each xi is exponential, and we already derived the exponential moment generating function, phi xi of s is equal to lambda over lambda minus s. And now W, which is the IID sum, is going to be phi x1 of s product through phi xn of s. And since all these moment generating functions are the same, this is phi xi of s raised to the power n. In other words, it's lambda over lambda minus s raised to the power n. I seem to have lost my exponent n here, but once it's in place, the rest of the proof just relies on either calculating or knowing that this is the moment generating function for the random variable w, which has this Erlang PDF. For example, here, we simply reference table 9.1 in the text that the table says that this indeed is the moment generating function of an Erlang random variable. This A here signifies two quizzes in this section. The first quiz is about discrete uniform random variables and calculating an MGF of the sum. It's good exercise if you need the practice, but it's also a little bit tedious. The solution follows. The quiz that follows this, the B quiz, is a sum of Gaussian random variables, and it's also a little bit complicated, but eminently doable.